So please give me the game scores because I know y'all be watching the game while I give the lecture, okay? Do I sound like a robot now? I'm paranoid.
No, it's really good. It's
Okay then.
cool.
Okay then. So today I know everyone probably takes some quant methods or something. This is our lecture where we talk about statistical significance and some related concepts. But I'm going to do my best to teach it in a more intuitive way to give you some understanding of like just how you think about it. My goal is for you to be able to think about these things. If you like to know more, go read on it. And then maybe talk if you're at a research center or a UX researcher and someone runs this, I want you to all be able to just understand these sorts of concepts and not use them mistakenly. You're not going to get an expert in stats, but you can run some basic ideas and at least know, let's say, what a p-value means. Okay? So that's what today is. So we're going to start with the two important concepts generally. So in a lot of our research as a data scientist, we want to understand the world. And for example, we might ask the question, how many hours do people spend gaming each day, right? And then we might ask, does a new feature change how long users stay in one app? We can then ask, is this thing that we're seeing, whether that's increasing how long they're staying in the app, is it real or is it just some noise, right? Is it just randomness? It's an important question, right? And for example, let's say I'm Iranian and a lot of people here are Canadian, right? Can you just take my height, let's say 183, and then one Canadian person that's, let's say 160, and then you say, oh, the difference between Iranians and Canadians is 20 centimeters, right? That's the idea. Is it noise? This difference between me and then one Canadian is noise, right? And then if you increase the sample size, it gets better, but it's still noise. So you have to think about whether these differences that you see are real or not, right? So we need data, but we can never measure everyone. That's the idea. So a population is the complete group you care about. But we just did the census. That's as complete as it gets. That's the population. For example, every gamer on the planet, all users on an app, every possible run of an experiment, everything. Places are usually too large to measure directly, too expensive to do it. We work with samples. Now, there's a whole story about how we sample. I'm going to skip it. But the idea is that we don't sample just how we want. It's like we don't just go on the street and find people that are close to us or talk to our friends. A sample, when we talk about it, is called a random sample generally for these types of studies, right? A random sample is something where you go and you pick people as random as possible and then think about some measurements, okay? So this is the subset of a population we actually observe, and we use the sample to estimate what the population looks like. So then we take for example, we're interested in the average of something for a population. We say, okay, the sample mean, X bar, estimates the population mean, right? So we use the sample as an estimate for the population. And this idea, this gap that always will exist because the sample is never the actual population, is called the sampling error because it never fully disappears. You will have some noise, some errors in your data, okay? So let's look at this little app that we can look, right? So let's say we have 200 gamers, each circle one person, and we want to look at the daily gaming hours, okay? So let's start with a really small sample, 5. This true mean is 2.86, right? But because we're only picking 5 people, right, the mean is different. It's a sample, but it's a small sample, right? We can keep picking different people from this 200, and as you can see, based on chance, this mean is being different, okay? You see how this line moves? Because randomness exists, because we have a small sample size. Let's take it to 80. See, it gets closer to the actual value because we take more at random. We know that the more we take randomly, the mean of the random sample would get closer to the mean of the population. That's a very important concept that you want to understand. That's why they say increase the sample size. That's why you never go and say, hey, my uncle smoked until he was 90 years old, right? He didn't die, so smoking doesn't kill. That's why you don't go with anecdotes, right? That's why you want to have more samples in your study, okay? So each drug gives a different mean, even from the same population. Small samples means we jump around widely. Large means that it clustered around the mean. And the dot plot was basically called the sampling distribution of it, okay? The variability is not a mistake. It's the nature of the sampling. How much variability should we expect by chance, right? That's the question that we ask. Now, another type of question is that imagine now we have two groups deliberately chosen, right? We have casual gamers and we have competitive league players. We want to look at their differences. We can sample both and find group B's mean is higher. But we just saw that samples vary even when nothing is different, okay? Maybe group B genuinely plays more, or maybe we just have a lucky draw. That is the general question, the sort of the type of question you ask in statistics. We need a principled way to decide, and we call that hypothesis testing. We start with the concept of the null hypothesis. We observe a difference. The idea of a null hypothesis is that we see some difference between these two groups, right? The example I gave was Iranian heights versus Canadian heights. Okay, we see some difference, right? And then we want to see whether this difference is actually true or whether it's based on this variability and this randomness that I showed. So group B had a higher average gaming in this example, and then our instinct is that the league caused them to play more. A reasonable hypothesis, but we want to test it. But before we claim that, we need to ask a harder question. So look at this visualization. Is this observed difference between these two samples? So this is the mean of the group competitive people. This is the mean of the casual gamers, right? Is this difference actually the reality? Because you might think, for example, that, hey, casual gamers are on their mobile phones, they play even more hours. That's another alternative hypothesis. The null hypothesis says there is no real difference. Any gap between the two sample means is just sampling variability. In other words, what we observe is to random variability. So this null hypothesis is not a claim we believe. We ask, how likely is that? Is it for us to see this difference given, remember how we talk about given, that the null hypothesis is true? So we're going to see examples of, but try to visualize it for yourself. How likely is it for me to see this difference between these two groups if this difference didn't really exist? Now we're going to look at how we can think about this, okay? So again, we're going to look at this idea, this difference between sample A and B, and say, okay, is any difference noise? So again, this is just a model, right? For example, competitive players gain more is a verbal claim. It could be true for many different reasons, right? So this testing of null hypothesis rules out only one explanation. It doesn't prove our hypothesis. It says we're confident that this difference we're observing is not due to chance, okay? Again, you can't say p-value for, I'm going to talk about p-values, but you see a lot of people say, okay, p-value is 0, this proves our hypothesis. It doesn't. It says that we are confident that this is not due to chance. And that's basically how we test it, right? But think about it. What else could explain the difference? group B plays more hours because this causes more play, but we can say we have a selection bias, heavy players join the conversation. We have some age differences, that's a confound. Age causes people to play less or more. We might have measurement errors. Okay, there are a lot of things you can have. So rejecting the null hypothesis only means we find it unreasonable to believe that the difference we are observing is due to chance. That's basically what we are observing, okay? What we do not test is, did competitive players already play more before joining the league? Are competitive players systematically younger or have more free time? Did they over-report gaming hours because the league makes it feel significant? Is our sample representative? These are not the things that we respond to, okay? Now we get to the question of p-value. You've heard it, some of you might see it. The p-value is, again, we have observed the difference between these two groups. Again, the p-value for many different things, but let's focus on the idea that there's differences between these two groups, okay? We ask, if the null hypothesis were true, how often would we see a difference this large or larger? Think about it. If there was no difference and we just randomly picked from people, how often would we see this difference between these two groups? How often would we see differences of 10 hours between gamers if this was true? That is p-value, and we're going to look at the example. So the p-value, again, remember, is the probability of obtaining results at least as extreme as the observed results under the assumption that the null hypothesis, which again that says everything is due to chance, is correct. Okay, so this says there's no difference, and this is our observed difference, and this, like, how the area is the p-value. How likely is it for us to see it? But p-value is not the probability that null hypothesis is true. You can't say that p-value says is 0.5 or 0.05. That means there's a 5% chance that this is due to chance. Not the probability that your results was a fluke. Not the size and importance of the difference. Not the probability that your finding will replicate again. The p-value only answers one narrow question. How surprising is this data, assuming nothing is going on? So the smaller means it's really surprising to see this if there was not a real difference, right? If it's 0.01, say, oh, it's really surprising. It might still be true. I would be surprised if I see a difference like that. So remember, they will show you a threshold of 0.05. It's a convention. We call the result significant if that's the p-value. This means less than 5% chance of seeing this data if the null hypothesis was true. And this is just some guy, Fisher, who chose this. Some fields use different thresholds. Sometimes thresholds are not even good. And then this idea that significance is binary is not really true, but we use it for science, okay? Now, let's look at a more deep example of how we do this. So I created, you can go to this later, but I'm going to go over it. I'm going to try to create these explorable explanations for more important concepts for you. So when you go to this website, you can basically get some explanation on what a p-value is and how we calculate, okay? So again, we never get to measure everyone. So suppose we want to know how much people game, not these 200 people specifically, people in general. The trouble is obvious. We can't survey the whole planet, right? So assume for now that this 200 is everyone, right? On the x-axis, we see daily gaming hours. So we have some people who do 10, most people are between 0 and 2, okay? Now, the blue is the true average of everyone. Again, now this is our population. Let's look at a small sample. Okay? Taking a sample is like basically scooping a water from a lake and then trying to measure its temperature. So the idea is that I've shown you this before. You can see how scattered these are, right? So if I click here, that the means are scattered around this, right? I can keep picking 25 samples, 5 samples from this population, just keep picking, and oh, there's some of them that are closer to the mean, there's more of them that are closer, but it's very wide. Okay, now look at this. We pick more examples, right? And see these the means, the blue ones are the means of this sample that we picked. They're now more close to the true mean. So if I keep picking, we're gonna see a lot of means. This blue ones is the average of the orange ones, okay? It's closer to the true mean. So when we pick larger samples, the mean of those samples is gonna be closer to the mean of the population. This is, you might hear about it if you've taken a stats class. This is called the central limit theorem. Essentially, the pile of sample means settles into a bell curve, normal distribution. Always, it just tends to be true. Even though our population is not a normal distribution, this is true. If you look at the averages from a sample, take a bunch of times, the mean of the sample will be it will be a bell curve around the mean of the true population. This is just true always. The spread of it, we know what the spread is, depends on the size of the sample. It's quadruple the sample size and wobble half. So this is the idea. So you can try again. So we can try with 20 samples, see how spread out this is, right? And then we can clear it and just increase the sample size. And then click again, see, it's less wide. That's the idea of central limit theorem. A lot of statistics uses this concept for you to know how p-values and stuff. This is the basic of a lot of stats. Now, we were sampling many times from a populations. We can't do that, right? We get a single samples, 30 players. So the sampling distribution, the thing that tells us how much our number could be wobbled, is exactly what we need and exactly what we can see. The rest of this page is about some clever ways to think about how we can actually simulate that. Okay, so we treat our sample as a stand-in for the population and we resample. Now, we get to our question of what is the difference between two groups, right? So group B was the league players, group A is the casual players, right? This is the mean, 1.83 for the casual players. This is the mean, 2.76 for the league players. You see there is a difference between them, okay? 0.93 hours, they play more, okay? How do we think about this? We want to say, is this gap real or is this a kind of gap that log hands out, okay? So first, we imagine nothing is going on. To answer that, sometimes a method that we do is we can play the devil's advocate, assume the boring explanation is true, the two groups are really the same. And the gap we saw is a pure coincidence. Statisticians call this a null hypothesis, but I can just call this the skeptic's assumption, right? So look at this. This is everyone. You get rid of the group labels, right? So you deal the labels at random, right? So you say we had group A and group B, you keep picking, you put all of your data together, and you randomly pick from them. You reshuffle. If it was during the chance, you should see differences, right? So I reshuffle once, I look at the difference is close to 0. This is what we really saw. Let's keep reshuffling. See, it's showing us. We were randomly picking, again, I can reset it. We put group A and B together, and then we shuffle, and we see the difference. The difference is close to 0. We do this a bunch of times. We're doing it many times. The thing we saw from the league players versus the casual players was 0.93, right? But this random sampling is telling us a different story. Okay? The p-value is how many times we see differences at least equal to this or more, okay, from this distribution, from these cases. So we ran it 1,000 times, we only saw 0.002 times. We only saw 2 times that this fraction was true, okay? You can run it again, okay? We can run it again. These are, if we take all the groups together, I'm reiterating, it's not that difficult of a concept. You need to visualize it for yourself. We take everyone, put them together, pick, and then group them, just get them into two random halves, and then calculate the difference between them. If this difference that we saw was due to chance, we should see this amount of difference many times. And then this is how we look at it. So we do 1,000 shuffle, get 1 verdict. A small p-value is, it says luck almost never does this, which makes the skeptic say, oh, it's just chance. Hard to believe. We never say it's proven false, say it's hard to believe. Again, so you can run it yourself later and see. Okay? Now, forget this whole p-value. P-value says, whatever difference I observed, okay, how likely is it for me to observe this if there was nothing going on, okay? But there's another important concept. Is the difference I'm seeing really good? Is it an important difference? Is this something meaningful, okay? So this is called effect size. If the difference is really small, for example, 0.1, like if the difference is like 5 minutes, do we even care? Is it important? If you go to a research as a UX researcher, it says, oh, this new intervention I created only increased usage of the app by 15 seconds, but if 15 seconds is significant, they're going to be like, oh, who cares? 15 seconds is not important. That's the effect size, okay? So we can have a large effect size. That's the difference you care about. And we can have a small effect size, right? We have medium effect size. So there's different ways to look at effect sizes, right? One of them is Cohen's d, which basically looks at the differences of the two groups, right? Divided by the standard deviation of everyone together. You put everyone together, look at how spread this is, that's the Cohen's d. So this is just like a rule of thumb. You can say, okay, the difference is large, the difference is medium, the difference is small. Okay? So you can look at Cohen's d and see how that might work based on the variability within your data. Okay? So p-value says, is this different? I'm reiterating, is this difference due to chance? The effect size tells you, is this difference meaningful? Is it big enough? You don't always use Cohen's d. You say, okay, I know that, let's say if people are on my app 10 hours for some reason, that's good. Why? Because for some metric, I have domain knowledge, it's going to generate $10,000 for some reason. That is a good effect size. You can use that. Okay? Now, we do another type of resampling that's really useful for another idea. It's called sampling with replacement. Again, let's try to visualize it. Let's say that this is our sample. 1, 2, 3, 4, 5, 7, 9. These are the numbers that we have. With replacement means we assume that we can pick, let's say, person number 7 multiple times. Because there's probably gamers that are similar to me in the world. That's the idea, right? So you can pick me multiple times. It creates this idea that, oh, Messi scored a goal? Okay. Thank you. But pay attention to the p-value as well. It's going to be like this for the next month. Okay? So the idea of random with replacement is that we can pick a person multiple times because people similar to that person exist. So let's say we picked number 2 times, right? We see it twice. The other samplings that we do, we're not doing it with replacement. Okay? Because we only have one sample, we want to know how much our answer would bounce around if we could collect fresh samples over and over, treating our data as a stand-in population and drawing from it with replacement. This is called bootstrap. It's a bootstrapping method. Again, just remember the name. It's a good method. How do we do that? Why do we use it? So we can bootstrap from both groups. So we have group A. We keep picking, let's say, 20 samples from group A with replacement and from 2 with replacement. Then we calculate this difference every time, right? This is the difference between this line and this line. Every time we take a sample, we calculate it. So this time is another difference. See, this is the difference. This time is another difference. We keep picking with replacement from different groups, and we calculate the sample, the difference of those 2 groups. Okay? Boom. What does this tell us? It tells us a bunch of differences between these 2 groups. If you run it 1,000 times, right, we have this sense that the difference between these 2, if we take say 95% of these 2 differences were in this area, right? That tells us our confidence intervals. You see sometimes those lines, those error bars, this is one way of calculating them, okay? And it tells us that we're confident that the difference we are observing is between this number and this number. And that it's very unlikely, because this is more than 0, it says, okay, it looks significant, okay? It's another way of thinking about significance is look at the difference, maybe just do this method, and then look at how different they are. We do this in all sorts of different ways you're gonna see, okay? So this is our 95% confidence interval. So when we talk about it, just remember, it's not that complicated of a problem, okay? So yeah, you can, again, run this to see confidence intervals. Again, this was the sampling way of thinking about p-values. Statistics we do simulations. I like, because we have computers, we can do a lot of things. Before, they had these mathematical assumptions. If you take them, again, I'm not going to teach them. This is not a stats course. It's just so deep that it's no time to talk about it. But let's say if they assume that the data is normally distributed, then you would have these methods to get to these ideas without sampling. So you might have heard of t-test, which is about the difference with two means. Chi-square is for counts. Mann-Whitney is for ranks, and NOVA is for several groups. There you go. So that's we just do simulations sometimes to make fewer assumptions. Okay? Essentially, the p-value, look at these ideas, but the p-value is how often luck matches or beats what you actually saw. Hopefully this helps. Go back to this. Oh, the goal was offside. Damn. All right. It's okay. So yeah, it's here. The link is in the slides. But let's reiterate. We observed a difference between 2 groups. The p-value, what the difference could be, what differences would be due to chance. And then we can, again, I'm going to not go over these, but this is for you to look at later. If null hypothesis is true, that there is no difference, then the group labels are meaningless. We can shuffle them and recompute the difference over and over. The p-value is a fraction of shuffles where chance matched or beat what we actually saw, right? So that's sort of, it tells you the idea of how you do it. And then the confidence interval tells you how uncertain we are about the differences. We talked about effect sizes as well. The difference is unlikely by chance. That's the significant p-value. Says nothing about whether this difference matters. We might have 1,000 examples. We could have a very small p-value that might be very significant, right? This is just the sample size is the same data. So the p-value changes if we increase the sample size. We really want to show and talk about how big is the difference. For example, again, for two groups, we can do Cohen's d. D is a difference of mean divided by pooled standard deviation. I have the formula here for you. And this is, look at these two groups, look like this difference between them is larger. The difference between them is not as large. More overlap, smaller effect, less overlap, larger effect, okay? So we have an observed difference. We say p-value, is it real? Rule out that this is due to chance. Cohen d, we go, how big is it? We measure practical significance. You always want to report both. A result can be statistically significant and practically tiny. We're just testing. Okay? So, for example, a new UI reduced task time by 0.1 seconds. P-value was 0.001 at n equals 10,000. Do we care? No. It doesn't matter to users. Sometimes we might see a difference at 15%. It's not significant, so the difference might be due to chance. However, if we increase the sample size and see the same difference, then that's good finding. So yeah, the significance is the property of the test. Importance of the property is the effect size. They are not the same thing. And the power, right? So we might have, again, let's think about like power when they say you do power analysis. When the null hypothesis is true, but we reject it, right? We say p less than 0.5, but that was actually due to chance. That's a type 1 error. You just think, well, you might hear this, go back to this. If the hypothesis is true, but we miss it, we say the effect is real, but the you said p-value is larger than 5, okay? The power is the probability of detecting a real effect when it exists. So essentially, that's what we mean by power analysis. So what affects power? Sample size affects it. Effect size, we just talked about what effect size is, that affects it. The alpha threshold that we talked about affects it. So the conversion of the target that they talk about is power of 0.8. Again, these are just for you to remember. Accepting a 20% chance of missing the real effect. How many participants? Essentially, that's what it helps you to ask. Do I need to detect an effect of this size? You run it before your study, not after. And what to report? You say the test statistic, you have a p-value, you report an effect size, you report confidence interval of the effect size, how certain you are about it, and you say you have a sample size and achieved power. Is this study sensitive enough? So you have these, when you want to run an actual study, maybe some of you want to run a thesis or end up working in a company that does A/B testing, that's what you do. So the study, the work that you're doing does this, right? So the p-value alone is never the whole story. The link to the explorable is here. You can come on. Okay. All right. So now we get to linear regression. Okay? Let's change gears a certain time. So I'm changing the data set. We were talking about gaming. Let's think about whether we think doom scrolling affects productivity. Who thinks this is true? Who thinks doom scrolling just reduces productivity? We all think this is true. But is this the only thing that affects productivity? There are probably other things. What else? Yes, FIFA, for example, affects productivity, some external factors. Yes, I've seen people that do that while, like when we wake up and just use it. Okay? So just assume that this is the real data set, right? The more doom scrolling hours you have, the less productive you are, right? It looks like this is the productivity score. How do we summarize this trend? So the first model that we can do, we can say, okay, the average productivity is just the mean, just the average of every productivity value that we have. Is this a good model? How do we measure whether this is a good model, right? We measure residuals. The residuals are the difference between our observed value and our model. So we say, okay, if the doom scrolling was 1, and we think for everyone, the observation is this, it's actually 80 something, and our model says 58, the difference is our error, is the residual, right? Some are above, so some underestimate, some overestimate, right? So they can cancel each other out. To see whether our model is doing good, we take the square of them and we sum them. It's an always positive number and penalizes big errors more. We've already talked about this. We're reiterating. Then we try different models. So this is a different line. Still flat. The residuals are still large, but it's better than the previous one. We do more. Is this the best that we can do? Right? Still better. So this is still good, but we can still do better. Oh, this is the line. Okay? This is the best fit line. The least squared line. See? The idea that said OLS, you might hear about it, is just this. What is the line that has the least amount of squared residuals for the given data? Boom. That's the line. So wherever you go, so you can just go, the line tells you if I thought that someone was doing doom scrolling this much, you say that the productivity is this much, okay? If they were doom scrolling this much, you say that the productivity is this much, right? That's the model. Still gonna have errors, but it's the best we got based on the data and the type of model that we do. Okay? That is the idea of a linear regression. So it defines a line that minimizes the sum of squared residuals. The slope tells that for each extra hour of doom scrolling, productivity changes by beta 1 points. That's the slope of this. The intercept is the predicted productivity when doom scrolling is 0. So we need two numbers for a line. That is the intercept and how much, if we change 1, how much this productivity drop, that is the slope. These are the two things you want for a number, for a linear regression. So don't be scared. Slope is easy. Intercept is easy. The residuals remain. No line fits perfectly. This leftover is our error. Okay? So how do we see whether our model is good or not? That's the idea. You say, okay, what was the baseline model is the mean. You take all the residuals, you square them, and you sum them. What's the best model? The best line that you could draw, okay? You take the residuals, you sum them, right? So squared residual of mean is the total variation in the data itself. The SS fit is the variation left after we draw the line. The difference between them is what we explained, right? So we divide by the fit by the mean. That's the percentage that the line explains. The percentage that the line doesn't explain, and we take 1 minus that, gets us R squared, the percentage, the proportion of variation explained by the model. So let's say our model explained our data 91%. If R2 is 0, the line is no better than the mean. If R2 is 1, the line explains everything perfectly. Our model does 0.91, means doom scrolling explains 91% of the variation in productivity. There's 9% left for other things. Okay? Now, how do we do the p-value for the R squared? It's the same idea that I just showed you. We take a bunch of random points from the data, calculate the line, calculate the R2. Boom, boom, many times. And then we say, how many times do we observe R2s that are at least as good or better if this was due to chance? That's the idea. And then you say, okay, the p-value for my R squared is less than 5%. It's unlikely that I see this R squared with this data due to chance. Okay? The tail probability is the p-value for the model. Okay? Now, again, what does the slope tell us? It tells there's a weak relationship, there's a moderate relationship, there's a strong relationship between these two. So that's like an effect size. A shallow slope means the predictor has little influence. This is a doom scrolling is a predictor. Productivity is the thing that you want to predict. A steep slope means a small change in X, and doom scrolling produces a lot of change in Y. The sign tells you the direction. Is it negative? Is it positive? So this is called a coefficient, which is a slope. It is our estimate, just like the sample mean. Okay, now you guys are going to not run model for just one thing. You're going to do multiple regression. It's the same idea. Instead of running a line, you might fitting a line, you fit a plane over the data. So let's say this is doom scrolling, this is sleep hours, and how much both of them explain productivity. Okay? Now, each predictor has its own slope, its own coefficient. So beta 1 is the slope of the doom scrolling slice. So we're looking at the doom scrolling slice. And beta 2 is the slope of the sleep slice, right? How do we think about this when we have multiple things? That, okay, if we keep, let's say, doom scrolling constant, don't change it, and change sleep, how much does Y change? That's the coefficient. So holding constant means compare people who differ only on this variable. Okay? That's why coefficients change when you add more variables, because you have more things to explain everything, and these two affect each other. The doom scrolling slope changes when we add sleep. Why? Because doom scrolling and sleep are correlated themselves. People who doom scroll also sleep less. So simple regression conflates both effects into one slope. Multiple regression separates them. Each coefficient is purified by the other, essentially. We can have the p-value for a coefficient. You know the drill. You can run it multiple times, get the coefficient. How many times do you think that this is due to chance if you see this coefficient? The slope is 0. But the idea is now the difference is say, okay, what is the likelihood, the null hypothesis that the slope is 0? Okay, so you shuffle them, refit the full model, record this, and then, okay, do it many times. Again, a lot of these have formulas, but we're just going to think about it in terms of simulation. The idea is the same. So the tail probability is the p-value for the coefficient. So you see a bunch of different p-values. The idea for all of it is, how likely is it for me to see this if there was nothing going on, if this model was just a random model? Okay, so let's look at, you might see a table for these. The intercept is the baseline productivity. Doom scrolling, the coefficient says each extra hour scrolling minus 7.3 points in productivity. And the p-value says, I don't think this coefficient is due to chance. I think it's not that likely. For sleep, you might say a 0.3 He said, okay, it increases productivity the more you sleep. And exercise, you might see a coefficient, but the p-value might not be significant. Okay? So you think, oh, this might be due to chance. Okay? Each row is one predictor. The coefficient is the slope, how much y changes per unit of x, holding others constant. The p-value asks, could this slope be 0 by chance? So you can say, okay, doom scrolling and sleep are both significant. We don't think that these are due to chance. And exercise has 0.4. We cannot rule that out. Although I think this is random data, I think exercise has out. Okay. So we just had a statistics lens on linear regression. This is the simplest regression model. I've explained to you what regression models is. You want to predict a number from data. This was the statistics way of doing things. When we do run statistics, that you collect the data, you want to say, okay, is something affecting something else? You're asking a question from the data. The machine learning lens builds the same model, but the question is different, right? So we say, is this slope significantly different from 0? For machine learning, I care about how accurately does this model predict new data if it's never seen, okay? So if I show you, if tomorrow someone says, okay, I'm doom scrolling 8 hours, how good is this model? That's the idea of machine learning. The shift changes everything about how we evaluate the model. We don't do the whole sort of, we can do R squared and stuff, but what we care about for machine learning is this. We leave a few data points out, a percentage of them. We don't train the model using those. Then we give them to the model and we see how much error are we getting. We split the data before fitting anything. It's called the training set for the ones that we show the model. The test set, the model, we don't show it to the model. Then we fit a line. Then we ask, how well does it predict the test points? Because we have the true data, we can compare the difference between the prediction and the true data. That is the error. This simulates what might happen when the model meets new real-world data. Another example, again, it's the same idea, is I don't know, if there is certain amount of pollution in air, you might get more sick people. That's an example, right? Then you have a bunch of data, pollution and number of sick people during different days. For some of those days, you don't do it, right? You just say, okay, I'm gonna not show this in the model, to the model, train it and see whether this predicts it. And then tomorrow day, you have pollution numbers, and you know that your model was 90% accurate, or we had good precision, and you can, okay, today we think we're gonna have a ballpark of this, the model predicts we're gonna have 80 sick people because of pollution in the air, so we need to prepare for it. That's the idea of machine learning. So how we measure this prediction error, it's called loss. We measure error on the test set, and then, which is the data the model never saw. Each orange line is a prediction error on a test point. Similar to residuals, but this is something the model is not fit on. You compare to the actual prediction. So you say what the model predicted, and you compare to the actual data. And you use root mean squared errors. In the model lecture, I've shown to you how these are different. But you use this to calculate these into one number. It's the same units as the y here, so this is productivity points. The lower the root mean squared error, you have better predictions on unseen data. Okay? Another idea is the idea of overfitting. You can have this model, you can have this model that has less error, but you might have a model that just perfectly learns the training data, so it's like fitting on them. But if you show it something new, it might not do a good job. That's an overfit model. It will fail badly, so you want to not overfit, okay? The test set is our defense. It tells us whether we have gone too far. In ML, a model that fits perfectly on training data is a warning sign. If your model was like, oh, you're 99% sure this is correct, that's bad. Generally, you want them, that's probably an overfit. Okay. That is today's lecture. Any questions? You can go back to the slides. It's already on the website. You can go play with the explainable. Send me feedback. I'm gonna try. It takes me a long time, so if you guys don't use it, it's not useful for me. But I think you can go and look at these examples, share it with other people. It's a good way for you to have resources to learn about some of these concepts that might be complex for you. Try to go on YouTube, watch more videos on this. I think with this lecture, you have the knowledge to do more of the assignments. Next Monday, we're gonna run linear regression. We can do it on the same data. We're not in the business of torturing the students. You can bring the data set and work on it. The labs are for that, okay? For now, because next week you're gonna have the midterm exam as well. And that's it. Any other questions? We can talk about what the midterm exam will be as well. It's not going to be hard. There will be a course project after the midterm. We will define it. What else? No questions? Okay, but the general idea on the big portion of your exam, you need to go through the slides and the readings. These are mandatory. You should read it. I'm lenient on testing on it, but the midterm you will be asked some questions. A big chunk of it, which is less, I want to see how you think on these ideas, is we're going to give you a few scenarios. What do you mean quiz? Let me finish up. We're going to give you scenarios, and we're going to ask you to write down. We're going to ask you to write down how you would run a data science project on this. What things would you care about? What metrics? What model would you build? Etc. etc. On Tuesdays, we don't have quizzes because I'm not mandating y'all to show up on Tuesdays, but I'm so glad that a lot of you do because it makes lecturing not boring. Okay. I'm gonna stop sharing. We're gonna send announcements for the rest of the stuff.